We're going to talk about propagation of disturbances in space. So we have pulse or wave propagation. And the first thing I would like to ask is what it is that is propagating in space. So when you have a disturbance like this created here on a string that is attached to a wall, on one side of the string we hold it with our hand and we move it up and down, and we see that there's a bump that is traveling. So what we have done by moving the end of the string up and down is basically apply a force to cause a displacement on the elements of the string, so therefore we're doing work, and this is going to transport energy from one end to the other end by propagating this pulse. So it's not a amount of matter that is being transferred from one place to the other, but it is the transfer of energy we're talking about in pulse or wave propagation. In order to realize this propagation of pulses and waves, in the case of mechanical disturbances, mechanical waves, we have three requirements. We need a source. First, we need a source. Second, we need a medium. Third, we need an interaction mechanism between the elements of the medium in order to propagate the pulse. So in this example, the source is the hand that is performing this motion up and down once. The medium is the string, so this is the source. The string is the medium in which the pulse propagates, and then between the elements of the medium we have a physical connection. So the atoms and molecules are bonded together, so when you have the disturbance on one side, that is propagated to the neighboring elements through this physical connection between the elements. So what is the difference between a pulse and a wave? Well, if you have a single bump is a pulse. On the other hand, if you have a periodic disturbance, that's going to be a wave. So if this hand keeps moving up and down, what would happen? We would see this string elements going up and down, traveling like this periodically, and finally they would reach this side and we would have a wave. So this would be a wave. What we have here is a pulse. And how do we characterize these pulses or waves? Well, we have two things we can look at. That is the speed with which they propagate, and we can look at the maximum disturbance, that is the total height here, height of the pulse, that is amplitude A. Alright, so we have two parameters that characterize this pulse or wave: A, the amplitude, and B, the propagation speed. If you look at the shape of the pulse after it is created by the source, the shape of the pulse is basically not changing as it propagates in the medium. So we assume that the pulse shape is not affected during propagation of the pulse. Okay, now regarding these pulses and waves, we have two different types. We can talk about transverse pulses and waves versus longitudinal pulses and waves. What is a transverse pulse? If you look at the elements of the medium, you find that these string elements are moving up in order to generate this disturbance. At the same time, the pulse is propagating to the right. So we find that elements of the medium move perpendicular to the propagation direction. So that is, example is mechanical waves on a string. On the other hand, if you look at this example, we have compression and rarefaction of this spring, and the elements of the medium are coming closer and farther as the pulse propagates throughout the medium. So I see that the direction of motion of the elements of the spring are on the x-axis, and the propagation velocity is also on the x-axis. Therefore, what makes a pulse or a wave longitudinal is that the elements of the medium basically move parallel to the propagation direction. A good example of a longitudinal wave is sound wave. Sound waves are pressure waves, as we will find out in a few videos later on, and they are longitudinal. Basically, the pressure waves in which the disturbance is moving parallel to the direction of propagation. Now, I want to mathematically describe a pulse or a wave, so I look at the shape of this string for this mechanical pulse that I have created on it at time t is equal to 0. So here is the propagation velocity v, and here is the amplitude a, and I find that when x is equal to 0, the pulse has reached its maximum point. So there is a function f of x that describes the shape of this pulse, but in general there must be a function y as a function of x and t that describes what this pulse is doing for all times. So this is y of xt when t is equal to 0. And what do I find? F of 0, the shape of the pulse, tells me this must be equal to amplitude a, which is y of 0, 0. Now, since the shape of the pulse does not change, if I look at this pulse at a later time, in the time interval t, I find that there is a total distance traveled by the maximum point here, that is vt. So the maximum point is on the corresponding to a location x equals vt on the x-axis now. So after a time interval delta t is equal to t, I have the function f of x minus vt that describes the shape of the pulse. Why? Because when x is equal to vt, I must have f of 0 equals to a. F of 0 was a, f of 0 must be equal to a again because it's the same shape that is propagating in this medium. Alright, so therefore my function that describes the behavior of this pulse for all times and all places is of the form f of x minus vt. So if we are to describe this pulse for all times, then we use the wave function y of xt, and it possibly has two forms. It's either a function of x minus vt or a function of x plus vt. X minus vt if it is traveling in positive x direction, and f of x plus vt if it's traveling in negative x direction. So let me think about this for a moment. So if I had the pulse propagating to the left instead of to the right, I would find that I have this pulse after a time interval t. This has traveled a distance vt. On the x-axis at location x equals to minus vt, I must have the amplitude a. So f of 0 was a. That means f of x plus vt must be equal to a as well, because at time t I have x is equal to minus vt for the location of the maximum point. So that's why I have this form here. Now, if we are mathematically describing this pulse for a fixed time, just as we did here, if t is fixed, we have a function that describes just the shape of the pulse, y of x. This is called the waveform. On the other hand, so the waveform is describing the shape of the pulse. If I have the full description as a function of x at time, then I have the wave function that gives me the full mathematical description. So this observation is an important one for the form of the wave function. Let's demonstrate this with an example. We have a pulse moving to the right along the x-axis, represented by the wave function. Y of xt is 2 divided by x minus 3t parenthesis squared plus 1, where x and y are measured in centimeters and t is measured in seconds. Find the expressions for the wave function at 3 different times, t equals 0, 1 and 2 seconds. And I also added here what is the propagation speed and what is the amplitude of this pulse. So first of all, I would like to find the waveform. So I set y of x at t is equal to 0. I have 2 divided by x squared plus 1. Y of x at t is equal to 1. This is 2 divided by x minus 3 squared plus 1. And y of x at t is equal to 2. 2 divided by x minus 6 squared plus 1. So these are uh, the wave functions at these times, basically they're describing the waveform. So they are the waveforms. The shape of the pulse is 2 divided by x squared plus 1, described by this function, and it is just offset by a certain amount as we go to a time different than t is equal to 0. Now what is the propagation speed of this pulse? Y of xt is of the form f of x minus vt. And it must be, because it says it's moving in the positive x direction to the right along the x-axis. Therefore it must have this form f of x minus vt. So I can see from x minus 3t squared term here tells me the propagation speed must be equal to 3.0 centimeters per second. So that's the propagation speed. And now I would like to know what is the amplitude of this pulse. Since the shape of the pulse is not changing as it propagates, I can pick any of these waveforms. So I look at t is equal to 0, what is y of x at t is equal to 0? It is 2 divided by x squared plus 1. And how do I find the amplitude? It's the maximum point in the waveform. So I take a derivative with respect to x. 0 times x squared plus 1 minus 4x divided by x squared plus 1 squared. Set it equal to 0, I find that x must be 0. So when x is 0, what is y? 2 divided by 0 squared plus 1, it is 2 centimeters. That's the amplitude of this pulse, because it's the maximum point. Now I can take a look at a plot of this pulse at a certain point in time. For t is equal to 2 seconds, you can see here I have a plot of the pulse. So at t is equal to 2 seconds, the maximum point is at 6. So it's because I have traveled a total distance from here to here, the maximum point. The total distance I have traveled, delta x, is equal to 6 centimeters, which is 3 centimeters times 3 centimeters per second times 2 seconds. So that is Vt. And I see the amplitude here is corresponding to 2 centimeters. So this basically gives the full description of the shape of the pulse at this time. T is equal to 2 seconds.